Sorry about that, guys. So last thing that we left off with was just trying to calculate the standard entropy of the system. We know this reaction. Remember, that's the Haber process. That's really important for us to know for our AP test. Since ultimately we have done this in the past, and I'm pretty sure that we also don't have our books with us at home this weekend. So let's save this slide. This is slide number 27. So we have slide number 23 that we're doing at the beginning of class just to check your answers on Monday. And then this slide we will do together very quickly after we do slide 23. Okay. Heat that flows into or out of the system changes the entropy of the surroundings. So we've already talked about this in isothermal process. Remember, we can find the change in entropy by that ratio of my amount of heat that we have in the system over that temperature. And it's a constant temperature, remember, because this is an isothermal process. Iso, same, thermal, temperature, so same temperature. Now, the person that was in charge, hopefully we remember, is Clausius. So Clausius, again, is responsible for creating or thinking about this type of ratio. Now, the universe is composed of the system and the surroundings. So we think that the universe is composed of the system and the surroundings. So that means the change of entropy in the universe has to be equal to the change in entropy of the systems plus the change in entropy of the surroundings. So for spontaneous processes, where we've said that they are irreversible, the change in entropy of the universe is going to be greater than 0. That's why we say that the universe is always going to be moving towards disorder. Okay, well, we took Clausius's idea of change in entropy of the surroundings is equal to the heat that's lost by the system over temperature. So I'm just taking Clausius's idea of my heat of the system, heat that's being released by the system, over temperature. And I also know from chapter 5 that heat, Q, is also equivalent to the change in enthalpy for the system. So let's plug this in or substitute delta H in for the Q value up here. So if I do that, that would give me the change in entropy of the universe is equal to the change in entropy of the system plus change in entropy over temperature. Okay, but we could also go a bit further, and we do that just because we don't like anything in the denominator, really, in chemistry or in math. We just don't. So let's multiply both sides by negative T, negative temperature. If I multiply this side by negative temperature, I'm just going to be left with delta H. I see that here. If I multiply this by a negative temperature, that's where I get this minus T times the change in entropy of the system. But then I also have to come over here and multiply this side by negative T, and this negative T times delta S universe is going to be what's left over here. There's a reason that we're doing this. The reason is because this is what Gibbs did, and Gibbs has something that's super important in chemistry that he calls Gibbs free energy. So this negative T delta S universe, this is going to be now delta G. So this reaction right here, or this formula right here, is called the Gibbs free energy formula. And delta G is just equal to this. So really I can say delta G equals delta H system minus T times delta S system. Okay, so this is the same thing as delta G. Now, what does G really indicate? G is really just another way to talk about entropy for the universe. So if the entropy of the universe is positive, delta G is going to be negative. And that's because if delta S is positive and delta G equals a negative T times delta S, then that means delta S is positive, T is negative, so overall this entire thing has to be negative. So we say that when delta G is negative, a process is considered to be spontaneous, because if it's an irreversible process, we kind of think about that as having more of a negative connotation with it. Process is spontaneous. So when delta G is negative, a process is spontaneous. Again, what we just said, if delta G is negative, the forward reaction is spontaneous. Now remember, at the beginning of this chapter, we stated that if a forward reaction is spontaneous, the reverse reaction would be non-spontaneous. If delta G is at 0, if delta G equals 0, then that means that the system is going to be at equilibrium. And if delta G is positive, then the reaction is going to be spontaneous in the reverse direction. So that means that if delta G is positive, the forward reaction is going to be non-spontaneous. Okay, so ultimately, Gibbs came up with his own kind of variable, and he did that because for him, this G relates to the system alone, and it's avoiding having to look at the surroundings at all. So let's go back to this. I'm thinking about what's happening in the universe here, and it's really hard to get an idea of what's happening just to the system all by itself in terms of entropy and how the system is going to do or relate to the universe. Because when we were thinking about Clausius's idea, we're comparing surroundings and system. But in this idea, I'm really only looking at the system and how the system is going to affect the universe. So that's why Gibbs is creating his own variable G. Okay. In any spontaneous process, carried out at constant temperature and pressure, the free energy is always going to decrease. So again, we said that delta G will be negative if we have a spontaneous process. So an analogy between free energy change during a spontaneous reaction, and then an analogy to that could be the potential energy change when a boulder or a rock rolls down a hill. So this is just showing kind of our analogy here. So potential energy in a gravitational field will drive that boulder. So I have potential energy for this rock up here at the top of this hill. And ultimately that potential energy is what's going to drive that to come down and reach its equilibrium position here at the bottom point, or what they call here this valley. So this potential energy is going to drive the boulder down until it reaches a state of minimum potential energy down here at the bottom, because as it's moving, it's going to gain kinetic energy, gain, until it reaches its maximum kinetic energy, maximum speed down here. So similarly, the free energy of a chemical system will decrease until it reaches some type of minimal value or minimum value. And when this minimum value is reached, which is what we call equilibrium, then that's where I've come here. And it's super similar. Your book kind of just gave us at least these pictures, but it's very similar to thinking about a boulder rolling down a hill. So I have lots of potential energy as I'm at the top of this. And ultimately, as it rolls down this hill, it's going to converting its potential energy into kinetic energy until finally it gets to the point where it's at its minimum amount of potential energy. It's used all of its potential energy up into kinetic energy. The same thing happens in a reaction. I have a certain amount of free energy that the reactants are going to have, and eventually we're going to use all of that energy up, and once that free energy in that chemical system decreases, it's going to reach a particular minimum where that's where equilibrium is going to happen. It's going to be this nice balance here between the reactants and the products. Okay, so calculating free energy change. How do I calculate delta G? On this problem, I'm going to use my delta G is equal to delta H minus T times delta S. So ultimately, you're given everything that you need to know in this problem. I want you to try to do this problem by yourself using that formula. And then this is slide 34. We'll talk about your answer on Monday and make sure that we know how to do it. This is simple plug and chug, so I think that you can do this. Standard free energy changes, just like what we talked about with standard enthalpy in chapter 5. We talked about the same thing just a few minutes ago with delta S, change in entropy, standard change in entropy. Delta G is going to be the exact same thing. So if I want to find the standard free energy changes, I'm going to take the sum of my standard free energy changes of the products and subtract the sum of the standard free energy changes for the reactants. And again, N and M are just the coefficients. So we can have practice with this. That's all that this slide here is wanting us to do. So we'll do this one together on Monday as well. Just another way to show, same thing as what we just did with Gibbs free energy, but now we actually are calling that negative T delta S delta G. So if I'm thinking about it at standard free energy change, then I can think delta G is equal to delta H minus T delta S. Well, how does delta G, the standard free energy, change with temperature? There are two parts that we're going to need to know to determine how delta G is going to change. These two parts are delta H, which is going to be our enthalpy term. Well, we already know that H is just is enthalpy, so that makes sense. Delta T, my change in temperature, or temperature times change in entropy, we just call the entropy term. So free energy, delta G, is going to change based on whether these are positive or whether these are negative. So this chart, table 19.3, is super imperative for you to know. I guarantee that a multiple choice question on your AP test will be asking you, what will delta G's value be if delta S is positive and delta H is negative? And you better know that then delta G is going to be negative. So this chart is super, 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 super important. We'll talk more about this chart on Monday because I think I want to just stop here for your video. But I'm going to tell you this. Because this chart is super important on Monday, even before we do the problems, this needs to be known. And I'm telling you it needs to be known because at the beginning of class on Monday, I wouldn't be surprised if I would be asking you some questions about this chart, because it's so important that I want you to know this that you're probably going to have a quiz on it. Have a good weekend. Bye.